Max Planck, a name that resonates deeply within the scientific community, was a pivotal figure whose work laid the foundations for one of the most transformative periods in physics. To understand the magnitude of his contribution, it is essential to consider the state of physics before his groundbreaking discovery. Before Planck's momentous breakthrough, classical physics dominated the scientific landscape. It was an era where the understanding of the natural world seemed clear and concrete. Isaac Newton's laws of motion, formulated in the 17th century, had provided a comprehensive explanation of the behavior of objects in motion, from celestial bodies to falling apples. Newton's laws were the cornerstone of classical mechanics, a system that held sway over nearly every aspect of physics. For centuries, Newton's laws had stood unchallenged, and the world operated under their influence. Alongside Newton, James Clerk Maxwell's equations unified electricity and magnetism, forming what we now call electromagnetism. These equations showed that light itself was an electromagnetic wave, carrying both electric and magnetic fields through space. The understanding of light, waves, and forces was rooted in these classical theories, which governed much of the observable universe. The fundamental nature of the universe seemed to be within grasp, and scientists, philosophers, and mathematicians of the time believed that they were nearing the final chapters of physics. However, by the late 19th century, a series of anomalies began to surface, anomalies that classical physics could not explain. One of the most perplexing problems was the issue of blackbody radiation. A blackbody, in physics, is an idealized object that absorbs all incoming radiation, regardless of frequency, and emits radiation in a specific pattern when heated. The spectrum of radiation emitted by a blackbody was well studied and experimentally confirmed, but classical physics predicted something completely inconsistent with reality. Classical physics, relying on the laws of electromagnetism and thermodynamics, suggested that a blackbody should radiate an infinite amount of energy at shorter wavelengths, especially at higher temperatures. This phenomenon, known as the ultraviolet catastrophe, predicted that as the wavelength of radiation shrank, the energy emitted by a blackbody would grow without bound, leading to an infinite amount of radiation being emitted. This, of course, was not observed in reality. Instead, the actual radiation emitted by heated bodies, such as metals or even the sun, followed a specific curve, peaking at a certain wavelength and tapering off at shorter and longer wavelengths. The discrepancy between what classical physics predicted and what experiments showed became one of the most glaring contradictions in the field of physics. For many years, scientists struggled to resolve this issue. The prevailing belief was that classical physics could eventually account for the observed data with some modification. But despite decades of research, no satisfactory solution emerged. Scientists began to realize that the core principles that had governed classical physics might need to be revised or even replaced altogether. The quest for an explanation of blackbody radiation became one of the most important challenges in physics, and it was here that Max Planck entered the scene. Planck was a professor at the University of Berlin, a highly respected physicist and a scholar who was deeply entrenched in the study of thermodynamics and statistical mechanics. He was tasked with addressing the issue of blackbody radiation, but unlike his contemporaries, Planck took a completely different approach. He refused to accept the classical predictions without challenge. Instead of adjusting classical theories to fit the experimental data, he sought a new path, one that would explain the observed radiation while still remaining consistent with the known laws of thermodynamics. The moment of inspiration came when Planck made a bold and seemingly counterintuitive assumption that energy could only be emitted or absorbed in discrete packets rather than being continuous. He proposed that the energy of oscillators in a blackbody could only take on certain values proportional to their frequency. This hypothesis was revolutionary. Instead of treating energy as a smooth, continuous quantity, Planck's theory suggested that energy came in chunks or quanta. This was a direct challenge to the classical belief that energy could be infinitely divided. To explain this mathematically, Planck introduced a constant now famously known as Planck's constant, denoted by h. This constant was the key to understanding the quantization of energy. Planck's formula for blackbody radiation, which is now known as Planck's law, provided a precise match to experimental data. It showed that the energy radiated by a blackbody at different wavelengths followed a predictable curve, matching the observations of experimental physicists. Planck's theory resolved the ultraviolet catastrophe by placing a limit on the energy emitted by a blackbody at short wavelengths. Planck's discovery was profound in many ways. First, it marked the birth of quantum theory. By introducing the idea of energy quantization, Planck set the stage for the development of an entirely new framework for understanding the microworld of atoms and subatomic particles. But at the time, Planck did not fully appreciate the revolutionary nature of his work. His initial interpretation of the quantization of energy was a mathematical tool to make the experimental data fit with theory. He believed that this quantization was an artifact of the mathematics, a way to avoid the contradictions inherent in classical physics. He had no intention of overthrowing classical physics entirely. He merely wanted to resolve the issues of blackbody radiation. Yet, over time, Planck's work gained wider recognition. It did not take long for other physicists to realize the significance of Planck's discovery. Albert Einstein, in particular, would later build on Planck's ideas in his explanation of the photoelectric effect, which won him the Nobel Prize in 1921. Einstein's work showed that light itself could be treated as quantized, behaving like discrete particles or photons, in addition to behaving as a wave. This deepened the foundations of quantum mechanics, leading to the formulation of wave-particle duality and the eventual development of the full quantum theory. In the years that followed, many other key figures in physics, such as Niels Bohr, Werner Heisenberg, and Erwin Schrödinger, would expand upon Planck's work, culminating in the creation of quantum mechanics. The theory would explain the behavior of particles at the atomic and subatomic level, a realm that classical physics had failed to describe adequately. Max Planck's discovery was not just a theoretical breakthrough. It also had profound implications for technology. The development of quantum mechanics led to the creation of technologies that have shaped the modern world, from lasers and semiconductors to quantum computers and GPS systems. Planck's work, which started with the simple task of explaining blackbody radiation, ultimately unlocked the mysteries of the universe at its smallest scales and revolutionized the way we understand the natural world. Planck's legacy, however, goes beyond the discovery of quantum theory. His work demonstrated the power of scientific inquiry and the importance of challenging established ideas. Before Planck, the idea of quantized energy seemed outlandish to most scientists, but through persistence, ingenuity, and a willingness to embrace the unknown, Planck showed the world that great discoveries often come from the most unexpected places. To understand the significance of Planck's work, it is crucial to recognize that it wasn't just a solution to a specific problem. In physics, it was a paradigm shift. Classical physics, which had served as the foundation of science for centuries, could not explain all the phenomena of the natural world. Planck's work revealed that, at the smallest scales, the rules were different. The universe, it seemed, was governed not by the smooth and continuous laws of classical physics, but by the discrete and probabilistic rules of quantum mechanics. This realization forever altered the trajectory of physics and set the stage for the modern scientific era. Max Planck's contribution to physics cannot be overstated. His work, though initially seen as a mere correction to classical theory, turned out to be the key that unlocked a new era in scientific understanding. The day Max Planck introduced his theory of quantized energy, physics was forever transformed. The ripple effects of his work continue to resonate in every corner of science today. Max Planck's revolutionary breakthrough in 1900 laid the groundwork for the future of quantum mechanics, yet the implications of his discovery extend far beyond the realm of theoretical physics. The introduction of energy quantization and the birth of quantum theory reshaped not only the scientific community's understanding of the microscopic world, but also the direction of future research in physics. His work marked the day when physics, as it was traditionally understood, was divided into two distinct eras: classical and quantum physics. Prior to Planck's work, physics was grounded in classical mechanics, a framework built by figures such as Isaac Newton, who established the laws of motion, and James Clerk Maxwell, whose equations unified electricity and magnetism. Classical physics viewed the world in terms of continuous, deterministic processes. Objects in motion followed predictable paths, forces could be calculated precisely, and the behavior of light, heat, and sound were seen as phenomena governed by continuous quantities. These principles formed the bedrock of our understanding of the natural world. But, as the end of the 19th century approached, the emergence of inexplicable phenomena like blackbody radiation revealed the cracks in classical physics' ability to fully explain the workings of nature. The blackbody radiation problem, as discussed earlier, presented a severe challenge to the prevailing theories. Classical physics predicted that as the wavelength of radiation shortened, the energy emitted by a blackbody would increase infinitely, creating the so-called ultraviolet catastrophe. In reality, this did not happen. The radiation curve for blackbodies followed a specific, well-defined pattern, peaking at a certain wavelength and falling off at shorter and longer wavelengths. This discrepancy between theory and observation was so glaring that it became one of the most urgent problems for physicists to solve. Max Planck, recognizing the significance of this issue, approached the problem in an entirely novel way. Rather than attempting to adjust classical theory, he introduced a new paradigm by suggesting that energy was not emitted or absorbed in a continuous manner, as classical physics implied, but rather in discrete, quantized packets. This hypothesis would eventually form the cornerstone of quantum theory. Planck's idea was bold and counterintuitive. Energy was not infinitely divisible, but instead, it existed in fixed amounts, proportional to the frequency of radiation. This was a radical departure from everything that physicists of the time had believed about the nature of energy. To explain this mathematically, Planck introduced a new constant, h, now known as Planck's constant, which became the fundamental scale for the quantization of energy. His formula, Planck's law, provided a solution to the blackbody radiation problem, describing the energy emitted by a blackbody as a function of temperature and wavelength. It was a triumph of both theory and mathematics, fitting experimental data with remarkable precision. In essence, Planck's work did not simply resolve a specific problem, it opened a gateway to an entirely new way of thinking about the physical world. The quantum leap introduced by Planck's discovery would not have been fully appreciated by him at the time. Initially, Planck saw his theory as a mathematical tool, a method to make the experimental data fit with existing theory. He did not immediately recognize the full philosophical implications of his work. It was only later, as other physicists like Albert Einstein, Niels Bohr, and Werner Heisenberg began to build upon Planck's ideas, that the true scope of quantum theory started to take shape. One of the key figures to extend Planck's work was Albert Einstein. In 1905, Einstein used Planck's idea of quantized energy to explain the photoelectric effect, in which light striking a metal surface could eject electrons from it. Classical physics had no satisfactory explanation for this phenomenon, but by treating light as being made up of quantized particles, which he called quanta, or photons, Einstein was able to show that energy was transferred in discrete packets, in alignment with Planck's hypothesis. Einstein's explanation of the photoelectric effect earned him the Nobel Prize in Physics in 1921 and further cemented the idea of quantization in the scientific community. Niels Bohr, another key figure in the development of quantum theory, would build upon Planck's and Einstein's work to explain the structure of the atom. Bohr's model of the atom, proposed in 1913, suggested that electrons orbit the nucleus in discrete energy levels, rather than continuously. This was a direct application of the concept of quantization introduced by Planck. Bohr's model was a revolutionary step in understanding atomic structure, and it was the beginning of a whole new chapter in atomic physics. Planck's discovery also had a profound impact on the philosophy of science. Before quantum theory, the scientific worldview was deeply rooted in determinism, the belief that the universe operated like a giant machine, governed by fixed laws of nature. Classical physics supported this worldview, as it suggested that if we knew the current state of a system, we could predict its future behavior with certainty. However, quantum mechanics shattered this certainty. It introduced a probabilistic model of the universe where the behavior of particles was not determined with absolute precision but could only be predicted with probabilities. The Heisenberg uncertainty principle, which stated that one could not simultaneously measure both the position and momentum of a particle with absolute accuracy, further emphasized this inherent uncertainty in nature. This probabilistic nature of quantum mechanics challenged the very way scientists thought about reality. It suggested that at the most fundamental level, the universe was not as deterministic as once thought. Instead, it was governed by uncertainty and chance. This realization led to a philosophical debate about the nature of reality itself, whether the quantum world was a true reflection of nature, or whether it was simply a mathematical model that described how we could predict the outcomes of experiments. In addition to its theoretical significance, Planck's discovery also had far-reaching technological implications. The development of quantum theory enabled the creation of technologies that have fundamentally transformed our world. One of the most important inventions based on quantum mechanics, the transistor, which is the building block of modern electronics. The principles of quantum mechanics also underpin technologies such as lasers, magnetic resonance imaging, MRI, and even the Global Positioning System, GPS. Quantum theory has also played a crucial role in the development of semiconductor technology, which has fueled the digital revolution and the rise of computers and smartphones. Even more recently, quantum mechanics has paved the way for the development of quantum computing. Quantum computers, which rely on the principles of superposition and entanglement, promise to revolutionize the field of computing, offering the potential to solve problems that are currently beyond the reach of classical computers. These developments are the direct descendants of Planck's original insight into the quantization of energy. Max Planck's work is a testament to the power of scientific inquiry and the ability of a single idea to reshape our understanding of the universe. His discovery marked the birth of quantum mechanics, a theory that continued to evolve and influence nearly every aspect of modern science and technology. Planck's role in the quantum revolution was not merely as a solver of a specific problem. It was as a visionary who helped redefine the very nature of reality itself. Today, Max Planck's legacy lives on in the continuing exploration of the quantum world as physicists continue to unravel the mysteries of particles, forces, and the fundamental structure of the universe. The world of quantum mechanics, with its strange and counterintuitive behavior, owes much of its existence to Planck's willingness to think beyond the boundaries of classical physics. The day Max Planck introduced the concept of energy quantization, physics was irrevocably divided into two worlds: the classical world, which described the macroscopic phenomena we observe in our daily lives, and the quantum world, a strange, unpredictable realm of particles and waves where the rules of reality as we know them no longer apply. This division has shaped the course of scientific progress for over a century, and it is likely that the profound implications of Planck's discovery will continue to unfold for generations to come. Classical physics, the framework that dominated scientific thought for centuries, was built upon the laws of motion, gravity, and electromagnetic theory. It provided an elegant and comprehensive explanation for the majority of observable phenomena in the natural world, developed by intellectual giants such as Isaac Newton, James Clerk Maxwell, and others. Classical physics was the science of order, determinism, and predictability. It successfully described the motion of planets, the behavior of light and heat, and the physical forces governing matter. For hundreds of years, this system held firm, shaping our understanding of the universe. At the heart of classical physics was the assumption that the world operated in a continuous, predictable manner. Whether it was the motion of an apple falling from a tree, or the gravitational pull between two bodies, classical physics was grounded in determinism. This view, primarily formed by Newton's laws of motion and the theory of gravitation, posited that the state of any system could be determined by its position, velocity, and the forces acting on it. These principles allowed scientists to predict the future behavior of objects with remarkable precision. Additionally, Maxwell's equations in electromagnetism beautifully describe the behavior of electric and magnetic fields. They unified previously distinct phenomena, electricity, magnetism, and light, into a single theory, creating a framework that could explain electromagnetic waves, including light. According to classical physics, light was treated as a wave, a continuous oscillation of electric and magnetic fields propagating through space. This view of light and its interaction with matter was fundamental to the scientific worldview in the 19th century. Despite its successes, however, classical physics began to reveal its limitations toward the end of the 19th century. A number of phenomena arose that could not be explained within the classical framework, raising questions that would challenge the very foundations of physics itself. One of the most significant of these was the problem of blackbody radiation. A blackbody is an idealized object that absorbs all incident radiation and re-emits it. The spectrum of radiation emitted by a blackbody is a critical concept in thermodynamics and electromagnetism. When a blackbody is heated, it emits radiation across a range of wavelengths, with the intensity of radiation peaking at a certain wavelength that depends on the temperature of the body. Classical physics, however, failed to predict the correct behavior of blackbody radiation. According to classical theory, the radiation emitted by a blackbody should increase without bound at shorter wavelengths, particularly in the ultraviolet range. This was known as the ultraviolet catastrophe, a result predicted by the Rayleigh-Jeans law, derived from classical principles. The problem was that this prediction contradicted experimental observation. In reality, as the wavelength of emitted radiation became shorter, the intensity of the radiation actually began to decrease, and the observed spectrum followed a very specific pattern. Classical physics, relying on continuous energy transfer and predictions based on the laws of electromagnetism and thermodynamics, could not explain why the radiation did not become infinite at short wavelengths. This discrepancy left scientists stumped, and the ultraviolet catastrophe became one of the most significant unsolved problems in physics at the time. Enter Max Planck, a German theoretical physicist who would soon embark on a journey that would reshape our understanding of the very nature of energy and matter. Tasked with solving the problem of blackbody radiation, Planck set out to reconcile the discrepancies between theory and observation. Planck's solution, however, was nothing short of revolutionary. Instead of tweaking the existing classical theories, Planck proposed a new idea. He suggested that energy could not be emitted or absorbed in a continuous fashion, as classical physics had always assumed. Instead, he postulated that energy could only exist in discrete packets or quanta. The idea, introduced in 1900, was the birth of quantum theory. Planck proposed that the energy of oscillators within a blackbody could only take on specific values, which were proportional to the frequency of the radiation. He introduced a new constant, now known as Planck's constant, denoted by h, to relate the energy of these quanta to their frequency. Planck's law, derived from this insight, successfully described the observed blackbody radiation spectrum and provided a solution to the ultraviolet catastrophe. At the time, Planck did not fully realize the profound implications of his discovery. He viewed the quantization of energy more as a mathematical tool, a necessary correction to existing theories, to match the experimental data rather than a fundamental change in the way energy itself behaved. Planck's law became the first major step toward a new era in physics. Though he did not yet recognize it, his work laid the groundwork for the quantum revolution that would completely overhaul the scientific understanding of the microworld. The quantization of energy was a radical departure from the continuous nature of classical physics. Classical theory had assumed that energy could be arbitrarily divided into smaller and smaller amounts, allowing for the precise transfer of energy in an infinite number of ways. But Planck's theory suggested that energy existed in fixed amounts quanta that could not be subdivided further. This insight opened the door to a new understanding of the microscopic world, where phenomena no longer followed the smooth, deterministic laws of classical physics, but instead operated on a probabilistic, discontinuous scale. Max Planck's work marked the beginning of the quantum revolution, but it was not until later that the full implications of his discovery would become clear. Planck's ideas would influence many of the great physicists who followed, including Albert Einstein, Niels Bohr, and Werner Heisenberg, who would take Planck's work further and develop the comprehensive theory of quantum mechanics. Einstein, in particular, would build on Planck's ideas in his explanation of the photoelectric effect, a phenomenon in which light shining on a metal surface causes the emission of electrons. Classical physics had failed to explain this effect, as it predicted that the energy of emitted electrons should depend on the intensity of the light, not its frequency. However, by treating light as quantized particles, photons, Einstein was able to show that the energy of the emitted electrons depended on the frequency of the light, aligning with Planck's concept of energy quanta. This groundbreaking work earned Einstein the Nobel Prize in Physics in 1921 and solidified the concept of quantization in the scientific community. It is crucial to recognize that the concept of quantization did not immediately replace classical physics, rather, it complemented it. Classical physics remained highly successful in explaining the behavior of macroscopic systems, such as the motion of planets or the behavior of gases. But the realm of the very small, the microscopic world of atoms and subatomic particles, could not be understood without the new principles introduced by Planck. This separation of scales, the classical for large objects and the quantum for microscopic phenomena, became a defining feature of modern physics. As quantum theory developed, the worldview of scientists was fundamentally transformed. The deterministic universe of classical physics, where everything could be known with certainty if enough information was provided, was replaced by a probabilistic universe, where outcomes could only be predicted with a certain probability. This new understanding of nature, driven by Planck's ideas, would lead to groundbreaking discoveries in atomic physics, particle physics, and later quantum mechanics. In addition to the theoretical advancements, Planck's discovery also had far-reaching technological consequences. Quantum mechanics, born from his work, enabled the development of technologies that have revolutionized the modern world. From semiconductors and lasers to MRI machines and quantum computers, the applications of quantum theory are vast and transformative. These technologies, which rely on the principles of energy quantization, have not only changed the way we interact with the world, but have also ushered in the digital age. Max Planck's contribution to science cannot be overstated. His work in resolving the problem of blackbody radiation did not merely solve a specific scientific puzzle, it opened the door to an entirely new realm of physics, one that continues to influence the direction of research and technology today. Planck's introduction of energy quanta was the first step in the development of quantum mechanics, a theory that reshaped our understanding of the universe from its very foundation. In the decades following his discovery, Planck's work would inspire generations of scientists to think in new ways about energy, matter, and the fabric of reality itself. Planck's legacy lives on not just in the equations that bear his name, but in the continuing exploration of the quantum world. His willingness to challenge the established paradigms of classical physics and to think beyond the confines of the known world set the stage for the remarkable developments that would follow. Quantum mechanics, born from Planck's insights, has become one of the most successful and influential theories in the history of science, and its impact will continue to shape our understanding of the universe for centuries to come. Max Planck's discovery did not just mark the birth of quantum theory, it set in motion an intellectual revolution that fundamentally transformed our understanding of the universe. By introducing the idea of energy quantization, Planck opened the door to a new realm of physics, one that departed radically from classical physics, which had dominated scientific thought for centuries. In doing so, he unknowingly altered the course of science, creating a framework for understanding the microscopic world and laying the foundation for the quantum revolution that would come in the years that followed. The primary thrust of Planck's work was his attempt to solve the problem of blackbody radiation, a dilemma that had plagued scientists for years. Classical physics, relying on laws like the Rayleigh-Jeans law, predicted that the energy radiated by a blackbody would become infinite at shorter wavelengths, a phenomenon known as the ultraviolet catastrophe. In contrast, experimental data showed a specific curve for blackbody radiation that peaked at a certain wavelength and tapered off at higher and lower wavelengths. This discrepancy exposed a flaw in classical physics, a flaw that Planck's theory would soon resolve. Max Planck's introduction of energy quanta, a concept so radical that it defied the classical understanding of continuous energy, was the first step into the quantum world. By proposing that energy was not emitted or absorbed continuously, but in discrete packets, Planck overturned a fundamental assumption of classical physics. Energy, it seemed, was quantized. This concept, though initially seen by Planck himself as a mathematical convenience rather than a true reflection of the physical world, laid the groundwork for the emergence of quantum mechanics. It is important to note that Planck himself did not fully recognize the revolutionary nature of his work at the time. In fact, he viewed his discovery as a way to adjust the existing framework to fit the observed data. He believed that energy quantization was just a temporary solution to a specific problem, the blackbody radiation issue, rather than a profound insight into the nature of energy itself. However, As time passed and more physicists explored the implications of his work, it became clear that Planck's discovery was not just a fix for a single problem but a key to understanding the universe at its most fundamental level. Planck's work was an intellectual catalyst for an entire generation of scientists. His ideas would inspire the likes of Albert Einstein, Niels Bohr, and Werner Heisenberg, who would expand upon and refine the concepts introduced by Planck. For instance, Albert Einstein used Planck's quantum hypothesis to explain the photoelectric effect. In 1905, a phenomenon in which light striking a metal surface ejects electrons. Classical physics had no explanation for this, as it predicted that light's intensity, rather than its frequency, would determine the energy of ejected electrons. However, by treating light as quantized, Einstein was able to explain the photoelectric effect in terms of discrete energy packets, or photons. This work earned Einstein the Nobel Prize in Physics in 1921 and cemented the concept of quantization in the scientific community. Another important figure in the development of quantum theory was Niels Bohr, who extended Planck's ideas to the structure of the atom. Bohr's model of the atom, proposed in 1913, suggested that electrons orbited the nucleus in specific energy levels or shells, rather than moving in continuous orbits as classical physics would have predicted. This idea of quantized orbits was a direct application of Planck's principle of energy quantization, and it helped explain the spectral lines observed in atomic emissions. Bohr's work marked another milestone in the development of quantum theory, moving it from a mathematical abstraction to a model that could explain experimental results. In the years following Planck's discovery, the field of quantum mechanics would take shape. Figures like Werner Heisenberg, who formulated the uncertainty principle, and Erwin Schrödinger, who developed wave mechanics, would build upon Planck's early work. The development of quantum mechanics not only changed how physicists thought about the behavior of particles and waves, but also fundamentally altered the philosophical underpinnings of science. Classical physics, with its deterministic view of the universe, was replaced by a probabilistic model, where outcomes could only be predicted with a certain degree of uncertainty. This shift from determinism to probability was one of the most profound changes brought about by quantum mechanics. In classical physics, if we knew the initial conditions of a system, its position, velocity, and other relevant parameters, we could predict its future behavior with great precision. However, quantum mechanics introduced the idea that at the microscopic scale, particles did not have well-defined positions or velocities. Instead, their properties were described by wave functions, which provided the probabilities of finding a particle in a particular state. The famous Heisenberg uncertainty principle further solidified this view by stating that one could not simultaneously measure both the position and a momentum of a particle with perfect accuracy. This inherent uncertainty was not a limitation of measurement tools, but a fundamental feature of nature itself. The philosophical implications of quantum mechanics were profound. Classical physics had provided a deterministic worldview, one in which the universe could be understood through the application of fixed laws. Quantum mechanics, on the other hand, revealed a universe that was fundamentally uncertain and probabilistic. This realization sparked a debate about the nature of reality itself, whether the quantum world was truly the way nature behaves, or whether it was merely a mathematical model that described the outcomes of experiments. Some physicists, such as Albert Einstein, were uncomfortable with the probabilistic nature of quantum mechanics, famously remarking that God does not play dice with the universe. Others, like Niels Bohr, embraced the new theory, arguing that the uncertainty was an inherent part of nature. The discoveries stemming from Planck's work not only reshaped our understanding of the physical world, but also led to the development of revolutionary technologies. The principles of quantum mechanics have been applied to a wide range of technology, from semiconductors and lasers to MRI machines and quantum computers. The invention of the transistor, which is the basis of modern electronics, was made possible by the development of quantum theory. Similarly, technologies such as the laser and quantum computing rely on the principles of energy quantization, wave-particle duality, and quantum superposition, all of which were concepts first introduced in the wake of Planck's work. Perhaps one of the most exciting prospects of quantum theory lies in the development of quantum computing. Unlike classical computers, which process information in bits, each bit representing either a 0 or a 1, quantum computer use quantum bits, or qubits, which can exist in multiple states simultaneously thanks to the principle of superposition. This allows quantum computers to process information exponentially faster than classical computers, potentially revolutionizing fields such as cryptography, drug discovery, and artificial intelligence. The ongoing research into quantum computing is a testament to the lasting impact of Planck's discovery. Planck's discovery also marked a turning point in the philosophy of science. Before the advent of quantum mechanics, science was largely built on the assumption that the universe operated in a deterministic manner governed by precise mathematical laws. Quantum mechanics, however, showed that, at the microscopic level, nature was governed by probability rather than certainty. This realization led to a shift in the scientific community, where the role of observation and measurement became a crucial part of understanding reality. It also highlighted the limits of human knowledge, as quantum mechanics introduced an inherent unpredictability into the behavior of particles. Max Planck's legacy is immense. His work set the stage for one of the most exciting and transformative periods in the history of physics, culminating in the development of quantum mechanics. Today, his ideas continue to shape our understanding of the universe, influencing everything from the smallest subatomic particles to the largest cosmological structures. The world that Planck uncovered, with its strange and counterintuitive rules, is still being explored, and the questions he raised continue to drive research in physics. In conclusion, Max Planck's discovery was not just a solution to a specific problem. It was the catalyst for an entire paradigm shift in physics. By introducing the concept of quantized energy, Planck opened the door to the quantum world, a world that has revolutionized our understanding of nature and led to groundbreaking technological advancements. The quantum revolution that Planck initiated has had a profound and lasting impact on science and technology, and it will continue to shape the future of physics for generations to come. In the early 20th century, physics was on the cusp of a profound transformation. Classical physics, long regarded as the final word on how the universe operated, faced an insurmountable challenge with the problem of blackbody radiation. Classical theories, which had explained macroscopic phenomena with remarkable precision, could not address the subtle intricacies of the microscopic world. One of the key issues was blackbody radiation, a topic that plagued the scientific community for decades. This is where Max Planck, a German physicist, would step in and offer a solution that would not only solve a long-standing problem, but also lead to the birth of quantum theory. Planck was attempting to resolve a paradox in thermodynamics and electromagnetic theory. Blackbody radiation describes the way a perfect emitter and absorber of radiation, an idealized object known as a blackbody, radiates energy when heated. Classical physics, however, had predicted that at shorter wavelengths, particularly in the ultraviolet range, the emitted radiation would increase without bound, ultimately leading to infinite energy, a result that was not observed in nature. This contradiction was known as the ultraviolet catastrophe. Despite many years of research and proposed modifications to existing theories, no satisfactory explanation emerged. This was the problem that Max Planck sought to address when he introduced a revolutionary concept: energy is quantized. Planck's assumption was radical. Instead of believing that energy could be transferred in any amount, as classical theory suggested, he proposed that energy was carried in discrete packets, which he called quanta. This idea was far removed from the continuous nature of energy suggested by classical physics. Planck theorized that the energy of oscillators in a blackbody, the fundamental units responsible for radiation, could only take certain values, specifically in integer multiples of a fixed amount. To put it simply, energy was not infinitely divisible, it came in small fixed units. This idea of quantization was unheard of at the time and directly contradicted the established understanding of the natural world. Classical physics, based on the continuous nature of energy, had worked remarkably well in most areas of science, from mechanics to electromagnetism. It was only when dealing with phenomena on the atomic and subatomic scales that these limitations became apparent. Planck's theory offered a resolution by applying a mathematical approach that allowed the theoretical curve for blackbody radiation to match the experimental data. This concept would prove to be the foundation of quantum mechanics. Though Planck initially thought of his work as a mathematical tool to solve a specific problem, his discovery would have far-reaching consequences. The introduction of quantization not only solved the issue of blackbody radiation, but also opened the door to a new way of thinking about the universe. The implications of energy quantization were soon recognized by other physicists, and in the years following Planck's discovery, quantum mechanics would begin to take shape. However, it was not immediately clear to Planck or others how profound this discovery would be. His ideas were more of a temporary solution rather than a dramatic break with classical physics. The legacy of Planck's work was immediately clear to the next generation of physicists. Albert Einstein, building on Planck's hypothesis, used the concept of quantization to explain the photoelectric effect in 1905. This phenomenon, where light striking a metal surface releases electrons, had been puzzling scientists, as classical theory could not explain the observed results. Einstein proposed that light, traditionally understood as a wave, also had a particle-like nature, with energy carried in quantized packets later called photons. This was a significant development, and earned Einstein the Nobel Prize in Physics in 1921. His work, along with Planck's, laid the groundwork for the development of quantum theory and heralded a new era in physics. At the same time, Niels Bohr, one of the most influential figures in quantum mechanics, expanded on Planck's work by introducing a quantized model of the atom. Bohr proposed that electrons in an atom could only occupy specific energy levels rather than a continuous range of orbits, as had been assumed in classical physics. This model of the atom not only explained the spectral lines of hydrogen but also incorporated the idea of energy quantization, building directly on Planck's original hypothesis. Bohr's work, along with that of others like Werner Heisenberg and Erwin Schrödinger, led to the full development of quantum mechanics in the 1920s. However, the shift from classical to quantum mechanics was not just a simple extension of existing knowledge. It was a radical departure from the way scientists had been taught to understand the universe. Classical physics, which had been built on the idea that the world was deterministic, governed by precise laws, was now being replaced by a probabilistic model of reality. Quantum mechanics introduced uncertainty and the idea that the behavior of particles could only be described in terms of probabilities, not certainties. This was a shocking idea for many physicists and sparked a series of philosophical debates about the nature of reality itself. One of the key figures in this debate was Werner Heisenberg, whose uncertainty principle introduced a fundamental limit to what could be known about a particle. According to the uncertainty principle, it is impossible to simultaneously know both the position and momentum of a particle with absolute precision. This was a direct challenge to the deterministic worldview that had dominated classical physics. If particles could not be precisely located or tracked, then the universe itself could not be fully understood in the way that classical physics had promised. This realization forced scientists to rethink their understanding of reality and the limits of human knowledge. Quantum mechanics, as a result, introduced a new worldview that was less about understanding the universe in precise, deterministic terms and more about dealing with probabilities, uncertainties, and statistical outcomes. This shift in perspective marked a dramatic change in the way scientists approached problems and the methods they used to understand the natural world. It was not just a theoretical advance, it was a fundamental change in the scientific methodology. As quantum theory evolved, it began to explain phenomena that were previously mysterious. For example, the behavior of electrons in atoms, which had been puzzling since the early 20th century, was now understood in terms of quantum mechanics. The spectral lines of elements, which had defied explanation in classical physics, were now accounted for through the concept of quantized energy levels. Similarly, the development of quantum mechanics helped to explain the strange behavior of particles in accelerators and the interactions between light and matter at the atomic scale. The success of quantum mechanics in explaining these phenomena led to a series of technological innovations. Quantum mechanics, which had begun as a theoretical construct to explain the behavior of energy, would go on to revolutionize technology. One of the most significant applications was in the development of semiconductors, the backbone of modern electronics. The principles of quantum mechanics also led to the development of laser, magnetic resonance imaging (MRI), and the field of quantum computing. These technologies, which have transformed our world, owe their existence to the breakthroughs made by Planck and other physicists who built on his work. Max Planck's contribution to physics was not just the resolution of a single scientific problem, it was the foundation upon which an entire new branch of physics was built. His introduction of energy quantization provided the first glimpse into the strange, probabilistic world of quantum mechanics, a world that operates according to fundamentally different rules than those of classical physics. This shift in understanding not only solved the blackbody radiation problem but also set the stage for an intellectual revolution that would change our view of the universe. Quantum mechanics has since become one of the most successful and powerful theories in the history of science. It has not only deepened our understanding of the universe at its smallest scales but has also led to innovations that have transformed technology and everyday life. The quantum revolution, which began with Max Planck's theory of energy quantization, continues to shape the future of science and technology, demonstrating the far-reaching impact of one scientist's bold idea. Max Planck's discovery in 1900 heralded the dawn of a new era in physics and science in general. His idea that energy is quantized fundamentally challenged the classical view of a continuous universe, laying the foundation for what would eventually become quantum mechanics. The breakthrough, though initially focused on the specific problem of blackbody radiation, led to a seismic shift in the way we understand the natural world. The discovery of energy quantization opened up an entirely new conceptual framework for how we describe the behavior of matter and energy on the microscopic scale. Planck's work wasn't just a theoretical breakthrough, it was a conceptual revolution, and it set in motion the most radical transformation of physics since Newtonian mechanics. Before Planck's work, the understanding of physics was firmly rooted in classical mechanics and electromagnetic theory. Classical physics had been incredibly successful in explaining phenomena that we can observe in our daily lives, from the motion of objects to the behavior of light and magnetism. It was based on the idea that energy and matter could be treated as continuous quantities that followed deterministic laws. Classical theories described the world as predictable, governed by fixed laws that could be mathematically modeled. This perspective, however, began to show its limitations when scientists encountered phenomena at the atomic and subatomic levels. The problem of blackbody radiation was one of the first signs that classical physics was not the complete answer. A blackbody is an idealized object that absorbs all radiation incident upon it and emits radiation in a characteristic spectrum. When heated, a blackbody emits radiation across a range of wavelengths. According to classical physics, however, the radiation emitted by a blackbody should increase without bound at shorter wavelengths, particularly in the ultraviolet range. This was known as the ultraviolet catastrophe. But when experimental data on blackbody radiation was analyzed, scientists found that the radiation followed a very specific pattern that did not match the predictions of classical theory. Instead of increasing infinitely at short wavelengths, the radiation intensity decreased after a certain point, forming a bell-shaped curve. Classical physics could not explain this observed behavior, and the result was one of the most significant unsolved problems in physics at the time. It was in this context that Max Planck entered the scene. Rather than making adjustments to the existing theories, Planck proposed a radically different idea. What if energy itself was not continuous? Planck hypothesized that energy could only be absorbed or emitted in discrete amounts, which he called quanta. This suggestion was not just a mathematical abstraction, it was a fundamental departure from everything scientists had previously understood about energy. Planck's assumption was that the oscillators responsible for radiation in a blackbody could only have specific energy level determined by their frequency, and these energy levels would be proportional to an integer multiple of a fixed amount. This constant, now known as Planck's constant, denoted as h, became the key to understanding energy quantization. The immediate result of Planck's hypothesis was the formulation of a new law now known as Planck's law of radiation. This law correctly described the observed spectrum of blackbody radiation, solving the problem that had stumped classical physics. The key insight in Planck's theory was that energy could not be emitted or absorbed continuously, but rather in small fixed packets or quanta. This was an entirely new way of thinking about energy, and it was an idea that, while initially met with skepticism, would go on to revolutionize the entire field of physics. Planck's work, at the time, was not immediately recognized as the radical break from classical physics that it would later prove to be. In fact, Planck himself initially thought of his theory as a mathematical convenience, a means to resolve a specific issue rather than a deep insight into the nature of energy itself. He saw energy quantization as a temporary tool to fix the blackbody radiation problem, not as a fundamental feature of the universe. Though Planck did not realize it at the time, his discovery would prove to be the cornerstone of a new theory, quantum mechanics, that would transform the entire landscape of physics. It was Planck's insight into energy quantization that paved the way for the development of quantum theory by subsequent physicists such as Albert Einstein, Niels Bohr, and Werner Heisenberg. Albert Einstein, for instance, used Planck's idea of quantization to explain the photoelectric effect in 1905. Einstein demonstrated that light, traditionally thought of as a wave, could also behave as a particle, with discrete energy packets called photons. This was a revolutionary idea, as it contradicted classical wave theory. Einstein's work on the photoelectric effect earned him the Nobel Prize in Physics in 1921 and gave strong empirical support to Planck's concept of energy quanta. Niels Bohr's work on atomic structure, developed in 1913, was another critical step forward. Bohr applied the concept of quantization to the behavior of electrons in atoms. He proposed that electrons could only occupy specific energy levels or orbits around the nucleus, rather than a continuous range of values as suggested by classical physics. Bohr's model successfully explained the spectral lines of hydrogen, provided further validation for the concept of quantized energy. The Bohr model, along with Planck's ideas, was instrumental in the early development of quantum mechanics. As quantum theory developed, it became clear that Planck's insight had far-reaching implications. It was not just a solution to a specific problem in blackbody radiation. It was a new way of understanding how energy and matter behaved on the smallest scales. One of the most profound consequences of quantum mechanics was its departure from the deterministic worldview of classical physics. Classical physics operated on the assumption that if we knew the state of a system, its position, velocity, and forces acting upon it, we could predict its future behavior with complete certainty. However, quantum mechanics introduced a probabilistic model where outcome could only be predicted in terms of probabilities, not certainties. This shift from determinism to probability was a fundamental change in how we understood the universe. The advent of quantum mechanics revealed that the behavior of particles at the atomic and subatomic level was not predictable with absolute certainty. Instead, particles existed in a state of probability, described by a wave function, which could only give the likelihood of finding a particle in a particular state. The Heisenberg uncertainty principle, formulated in 1927, reinforced this view, stating that it was impossible to simultaneously measure both the position and momentum of a particle with absolute precision. This uncertainty was not due to limitations in measurement tools, it was an intrinsic property of nature. The implications of Planck's work went far beyond theoretical physics. Quantum mechanics, based on Planck's ideas, would go on to shape the development of modern technology. Technologies such as semiconductors, lasers, and magnetic resonance imaging, MRI, rely on quantum principles. The invention of the transistor, which is the basis for modern electronics, owes its existence to the discoveries in quantum mechanics. Additionally, emerging technologies like quantum computers, which use the principles of superposition and entanglement, promise to revolutionize computing by solving problems that are currently intractable for classical computers. Max Planck's discovery was in many ways a point of no return for physics. It marked the beginning of a new era, in which the microscopic world was understood in terms of probabilities, quanta, and uncertainty. Planck's insight into the quantization of energy did not just resolve a specific scientific issue, it set in motion the creation of a new framework for understanding the universe, one that has since expanded into countless fields of research and technological innovation. The quantum revolution that began with Planck's work continues to shape the direction of modern science, demonstrating the enduring power of one physicist's bold leap of imagination. The birth of quantum mechanics, rooted in Max Planck's groundbreaking work in 1900, forever changed the way humans perceive the universe. Before this discovery, classical physics, with its deterministic view of nature, had dominated scientific thought for centuries. It was based on the idea that energy and matter behaved in continuous, predictable ways. Classical theories, like those proposed by Newton and Maxwell, could explain the motion of objects and the behavior of light in large-scale phenomena, but they struggled with microscopic phenomena, especially in the case of blackbody radiation. The problem of blackbody radiation was crucial because classical physics predicted that a blackbody, an object that absorbs all radiation falling on it, would emit infinite energy at higher frequencies, a prediction that was clearly at odds with experimental results. This issue, known as the ultraviolet catastrophe, was a key challenge that classical theories could not resolve. Max Planck, a German physicist, found a radical solution to this problem by introducing the idea that energy is not emitted or absorbed continuously, but in discrete packets or quanta. This insight was so revolutionary that Planck himself initially viewed it as a mathematical tool rather than a fundamental change to the understanding of the physical world. He proposed that energy could only exist in fixed amounts, proportional to the frequency of radiation. The concept of energy quantization, which was encapsulated in the introduction of Planck's constant, provided the key to solving the blackbody radiation problem. Planck's law, derived from his hypothesis, successfully matched the experimental data and eliminated the ultraviolet catastrophe. This was the moment when classical physics was definitively shown to be incomplete at the microscopic level. The quantum theory that emerged from Planck's work would evolve rapidly in the following years. Albert Einstein, using Planck's quantization hypothesis, was able to explain the photoelectric effect, where light striking a metal surface emitted electrons. This was an important extension of Planck's work because it suggested that light had both particle-like and wave-like properties, a concept known as wave-particle duality. It was a new way of thinking about light and energy, one that moved beyond the classical idea of light as a continuous electromagnetic wave. Einstein's work further solidified the importance of Planck's insight, and he would go on to win the Nobel Prize in Physics in 1921 for this explanation of the photoelectric effect. As the field progressed, the significance of Planck's discovery continued to unfold. Niels Bohr, a Danish physicist, applied the concept of quantization to the structure of the atom. He proposed that electrons orbit the nucleus in specific energy levels rather than a continuous range of orbits, and that the energy of an electron is quantized. This was another leap in understanding, demonstrating that not just energy, but also the very structure of matter at the atomic level was governed by quantum rules. Bohr's model of the atom explained the spectral lines of hydrogen and further demonstrated the power of Planck's insight. The development of quantum mechanics soon reached its full form, with figures like Heisenberg and Schrödinger making major contributions. Ultimately, Planck's work laid the foundation for one of the most successful, transformative theories in the history of science. Quantum mechanics not only solved the mysteries of the atom but also provided the framework for technologies that have revolutionized modern life. Lasers, semiconductors, and magnetic resonance imaging, MRI, are just a few of the technologies made possible by the principles of quantum theory. The quantum revolution, which began with Planck's introduction of energy quantization, has had a profound and lasting impact on both theoretical physics and practical technology, shaping the modern world in ways Planck could never have imagined. Max Planck's work in the early 20th century marked a revolutionary shift in the field of physics. Prior to his groundbreaking discovery, classical physics dominated the scientific landscape, providing a comprehensive explanation of the behavior of objects on a macroscopic scale. Classical theories, such as those formulated by Isaac Newton and James Clerk Maxwell, were based on the assumption that energy and matter operated in continuous, predictable ways. However, this view began to break down when scientists encountered phenomena on the atomic and subatomic levels, particularly with blackbody radiation. This phenomenon, which involved the emission of radiation by an idealized object known as a blackbody, presented a paradox that classical physics could not explain. The problem of blackbody radiation was famously known as the ultraviolet catastrophe. Classical physics, specifically the Rayleigh-Jeans law, predicted that a blackbody would emit infinite energy at shorter wavelengths, particularly in the ultraviolet range. In contrast, experimental data showed that the radiation emitted by a blackbody followed a specific, well-defined pattern, peaking at a certain wavelength and tapering off at shorter and longer wavelengths. This contradiction between theory and observation presented a major challenge to the scientific community, and no solution could be found using classical physics. Max Planck, a German physicist, approached this problem with a radically new perspective. He proposed that energy was not emitted or absorbed continuously, as classical physics suggested, but in discrete packets, which he called quanta. This idea, which was a departure from everything scientists had believed about energy, suggested that energy could only take specific values proportional to the frequency of radiation. To explain this, Planck introduced the concept of Planck's constant, a fundamental constant that tied the quantization of energy to the frequency of radiation. His formula, now known as Planck's law, provided an accurate description of black-body radiation, solving the ultraviolet catastrophe and validating his hypothesis of energy quantization. Planck's discovery was not only a solution to a specific problem, it laid the foundation for the development of quantum mechanics. The concept of quantization would go on to inspire subsequent physicists, including Albert Einstein, Niels Bohr, and Werner Heisenberg. Einstein, in particular, used Planck's work to explain the photoelectric effect, where light, striking a metal surface, emitted electrons. By treating light as composed of discrete packets of energy, photons, Einstein's work further cemented the idea of quantization and led to the development of the quantum theory of light. As the field of quantum mechanics developed, it radically transformed our understanding of the microscopic world. Classical physics, which had operated under the assumption of determinism and continuous energy, was now being replaced by a probabilistic model, where particles existed in a state of uncertainty and could only be described by probabilities. This shift marked the birth of a new era in physics, one that introduced concepts such as wave-particle duality, superposition, and entanglement, which would go on to challenge our understanding of the very nature of reality. The far-reaching implications of Planck's work extend beyond theoretical physics and into practical technology. Quantum mechanics has paved the way for the development of technologies such as lasers, semiconductors, and magnetic resonance imaging, MRI. The principles of quantum theory have revolutionized modern science and technology, enabling the creation of devices and systems that were once thought impossible. Planck's discovery, which began as a solution to a specific problem, eventually led to a transformation in how we understand the universe and how we harness the laws of nature for practical purposes. In conclusion, Max Planck's introduction of energy quantization marked the beginning of a new chapter in the history of science. His work not only solved a long-standing problem in physics, but also laid the groundwork for the development of quantum mechanics, a theory that continues to shape the modern world. Planck's discovery of quantized energy transformed our understanding of the atomic and subatomic worlds, giving birth to a new scientific framework that would change both the course of physics and the technologies that drive our world today. Max Planck's discovery in 1900 set the stage for one of the most transformative shifts in the history of science. Before his groundbreaking work, classical physics had provided a clear and predictable model for understanding the behavior of matter and energy. This framework, developed by great minds like Isaac Newton and James Clerk Maxwell, assumed that energy and matter behaved in continuous, deterministic ways. Classical physics successfully explained large-scale phenomena such as planetary motion and the propagation of light, but struggled to account for microscopic phenomena, particularly those related to black-body radiation. The problem of black-body radiation was a significant challenge to classical physics. A black-body is an idealized object that absorbs all incoming radiation and emits radiation based on its temperature. Classical theories, particularly the Rayleigh-Jeans law, predicted that as the wavelength of radiation shortened, the intensity of emitted radiation would increase without limit, especially at shorter wavelengths in the ultraviolet range. This prediction, known as the ultraviolet catastrophe, was not borne out by experimental data. In reality, the intensity of radiation emitted by a blackbody decreased at shorter wavelengths, defying classical prediction. This discrepancy presented a crisis in classical physics, as no explanation seemed to fit the observed data. Max Planck approached this dilemma by proposing a radical new idea: energy is not emitted or absorbed continuously, but in discrete units or quanta. This concept of energy quantization directly contradicted classical physics, which had treated energy as a continuous, infinitely divisible quantity. Planck's hypothesis was that the energy of oscillators in a blackbody could only take on specific values, each proportional to the frequency of the radiation. To explain this mathematically, Planck introduced a constant now known as Planck's constant, which became a fundamental element in the development of quantum theory. His formulation provided a successful explanation for blackbody radiation, solving the ultraviolet catastrophe and laying the groundwork for future advancements in physics. While Planck initially viewed his theory of quantization as a mathematical tool to resolve a specific problem, it would soon become apparent that his discovery was much more profound. Planck's work opened the door to a new era in physics, one where the behavior of energy and matter at the microscopic scale was governed by discrete, rather than continuous quantities. His insight would later inspire other physicists, including Albert Einstein, Niels Bohr, and Werner Heisenberg, who would extend and build upon his ideas to develop quantum mechanics. Einstein's work on the photoelectric effect in 1905 provided further evidence for Planck's hypothesis. Einstein showed that light, traditionally thought of as a continuous wave, could also behave as discrete particles, or photons. By applying the concept of energy quanta to light, Einstein was able to explain the photoelectric effect, where light striking a metal surface caused the emission of electrons. This was a pivotal moment in the development of quantum theory, as it showed that not only was energy quantized, but light itself exhibited particle-like properties. Einstein's work won him the Nobel Prize in Physics in 1920 and solidified the role of quantization in modern physics. At the same time, Niels Bohr applied Planck's concept of quantization to atomic structure. Bohr proposed that electrons in an atom could only occupy specific energy levels or orbits, rather than moving in a continuous range of paths. This model successfully explained the observed spectral lines of hydrogen, further confirming the validity of Planck's ideas. Bohr's atomic model marked a key milestone in the development of quantum mechanics and led to further advancements in understanding the behavior of matter at the atomic level. Max Planck's contributions did not just lead to theoretical advances, they also had profound practical implications. The development of quantum mechanics eventually gave rise to technologies that have revolutionized the modern world. Semiconductors, lasers, and MRI machines are just a few of the many applications based on quantum principles. The invention of the transistor, a fundamental component in modern electronics, was made possible by the development of quantum theory. Similarly, the development of lasers, which rely on the principles of stimulated emission of radiation, and MRI machines, which exploit the quantum properties of atomic nuclei, have transformed medicine, communication, and countless other fields. Planck's discovery also brought about a philosophical shift in how scientists viewed the universe. Classical physics had operated on the assumption that the universe was governed by fixed, deterministic laws, but quantum mechanics introduced a probabilistic model where outcomes were not certain, but could only be described in terms of probabilities. This shift from determinism to probability represented a fundamental change in how we understand the nature of reality itself. The inherent uncertainty introduced by quantum mechanics, exemplified by Heisenberg's uncertainty principle, challenged the deterministic worldview that had been the cornerstone of classical physics. In conclusion, Max Planck's introduction of energy quantization fundamentally changed our understanding of the universe. His work solved a long-standing problem in blackbody radiation and paved the way for the development of quantum mechanics, a theory that has become one of the most successful and influential in the history of science. Planck's ideas continue to shape both theoretical physics and technology today, providing the foundation for innovations that have transformed modern society. The quantum revolution that Planck initiated has had a profound and lasting impact on science, technology, and philosophy, and its influence will continue to be felt for generations to come. Max Planck's discovery in 1900 marked the beginning of a revolution in the field of physics, forever altering how scientists understood the nature of energy and matter. Before this breakthrough, classical physics had provided a robust framework for understanding large-scale phenomena, such as the motion of planets and the behavior of light. It was based on the assumption that energy and matter behaved in a continuous manner, and this view had been incredibly successful in explaining most of the observable universe. However, when scientists began to explore phenomena on a microscopic scale, such as the emission of radiation by a black body, classical theories began to falter. The problem of black-body radiation, also known as the ultraviolet catastrophe, was a major challenge for classical physics. A black body is an idealized object that absorbs all incident radiation and re-emits it. Classical physics, particularly the Rayleigh-Jeans law, predicted that a black body should emit infinite energy at shorter wavelengths, especially in the ultraviolet range, but this was not observed in reality. Experimental data showed that the radiation emitted by a black body followed a specific pattern, with the intensity peaking at a certain wavelength and then tapering off. This discrepancy between theory and experiment was a major puzzle that classical physics could not resolve. Max Planck's solution to this problem was nothing short of revolutionary. Instead of continuing with the assumption that energy could be emitted or absorbed continuously, Planck proposed that energy is quantized. This meant that energy could only exist in discrete packets, or quanta. Planck's insight was radical because it directly contradicted the classical belief that energy was continuous. To explain this, he introduced Planck's constant, a fundamental constant that would become a cornerstone of quantum theory. Planck's hypothesis provided a new mathematical formula, now known as Planck's law, which correctly described the radiation emitted by a black body and eliminated the ultraviolet catastrophe. This was the first step toward a new understanding of the microworld. While Planck's theory initially seemed like a mathematical tool to solve a specific problem, its implications were far-reaching. The idea of energy quantization would later inspire other scientists to extend it to different areas of physics. Albert Einstein, for example, used Planck's concept of quantization to explain the photoelectric effect in 1905, where light striking a metal surface emitted electrons. Einstein's work showed that light, traditionally considered a continuous wave, also had particle-like properties, which he called photons. This dual nature of light wave and particle was a major breakthrough that laid the foundation for quantum mechanics. Niels Bohr, another key figure in the development of quantum mechanics, built on Planck's work to develop a model of the atom. Bohr proposed that electrons in an atom could only occupy specific energy levels rather than moving in a continuous range of orbits. This quantization of electron orbits was consistent with Planck's idea that energy levels are discrete. Bohr's model of the atom helped explain the spectral lines observed in hydrogen and further validated Planck's ideas. Planck's discovery also challenged the deterministic worldview that had dominated classical physics. Classical mechanics, founded by figures like Newton, was based on the idea that if we knew the position and velocity of an object, we could predict its future behavior with certainty. But quantum mechanics introduced a probabilistic model of reality, where the outcomes of certain experiments could only be predicted in terms of probabilities, not certainties. This was a fundamental shift in how scientists viewed the nature of the universe, and it was exemplified by Heisenberg's uncertainty principle, which stated that one could never simultaneously measure both the position and momentum of a particle with absolute precision. In addition to the theoretical advancements, Planck's discovery had profound technological consequences. The development of quantum theory paved the way for technologies that have revolutionized the modern world. For example, semiconductors, which are the foundation of modern electronics, rely on principles of quantum mechanics. Lasers, which have applications in everything from communication to medicine, are based on quantum principles. Magnetic resonance imaging, MRI, a technology that has transformed medical diagnostics, also relies on the quantum properties of atomic nuclei. Planck's work ultimately led to the creation of quantum mechanics, a theory that has become one of the most successful in the history of science. Quantum mechanics has not only provided deep insights into the behavior of matter and energy at the atomic and subatomic levels, but also facilitated technological innovations that have changed the world. Today, quantum mechanics remains at the heart of scientific research, with applications ranging from quantum computing to advanced materials science, and its influence shows no sign of waning. Planck's introduction of energy quantization, which began as a solution to a specific scientific problem, has had far-reaching implications that continue to shape the future of science and technology.